Hi, Mr. Claxton's Algebra 2 CP class. We're looking at the complex numbers. All right? What have we done? The prerequisite knowledge that we will need is knowledge of our perfect squares and knowledge of when we simplified square roots by what I call rooting out the perfect squares. What are we doing now? Well, we are going to perform operations with pure imaginary numbers and perform operations with complex numbers both. So the first thing we're going to attack here is performing operations with pure imaginary numbers. In order to do that, we need to understand the cycle of I. Now, your book gives you a nice table, right? Really nice table. And it tells you these first two cycles. You see cycle 1 on top here and cycle 2 on the bottom. Looking at the cycles, you should be able, once you've defined the first two here, the first two complex numbers, that's I to the first and I squared. If you have those, then you can create any other imaginary number that's raised to a power. The recipe for this, just to get right to the point, the recipe, right, if this were a recipe, the directions would be divide the exponent by 4 and use the remainder or decimal point with the cycle of I. So that means that if your remainder, so if you're looking right down here, if your remainder is 1 or your decimal equivalent is 0.25, then it's going to be the power of I is going to be the same as I to the first, which is I. If your remainder is 2, decimal equivalent would be 0.5, then it's equal to I squared. And if the remainder is 3, decimal equivalent, 0.75, then it's equal to I. That's I to the third power. I know it looks like I to the fifth. Let me go ahead and make that a definite 3 there, definite 3. All right, and then if your remainder is 0, which in this case would be 4, okay, well, remainder 0, then the decimal equivalent of that is going to be 0, right? There is no remainder. The 4 was wrong there. If the remainder is 0, then the decimal equivalent, which you're going to see like 5.0 or 188.0. Up here we see 1,000.0. Then it's the same as I to the fourth, which is 1. So with that recipe, there are some examples here that we did run through in class. Example 1, example 2, and example 3. Notice the remainder there in example 3. The remainder is 0, not 4. The remainder is 0. So there are 3 groups of 4 in 12. 3.0, so this is equivalent to I to the fourth power, which is 1. So my answer then is 1. Okay, I to the 12th is equal to 1. Looking at a couple more examples, I to the 4,000th power equal to 1, I to the 237th power. And remember, the trick that I told you was look at the last two numbers. If the last two numbers are divisible by 2 or by 4, then the number will be divisible by 4. So that's 37. It's really close. Let's see, 36. Is 36 divisible by 4? Yes, it is. 36 divided by 4 is 9. So then I would know that this is just one more in that cycle, right? So I know that I to the 237th is going to have a remainder of 1, and therefore be equal to I to the first power, which is I. All right, so knowing the cycle of I, we really do need to hone in on the fact, of the first cycle. So looking back at the first cycle, as we simplify pure imaginary numbers, we're going to look back to this and refer back to this. We should be able to either derive this or memorize. I cubed is equal to negative I to the fourth is equal to 1, I squared is equal to negative 1. That is of supreme importance. This I squared right here, I will outline it twice. I squared equals negative 1. We will come back to that. So notice here, how we simplify. This is how we simplify the square roots. A nice color coding. The more difficult problems that you're going to encounter are 1 through 6 all on page 250. Now, looking at these problems, I want to start with, if you look at number 3. Okay, number 3. We are dealing with pure imaginary numbers. Pure imaginary numbers are numbers without any real part. They're complex numbers without any real part. They just have the imaginary part. So we have 4i times negative 3i. And in this case, we're just going to multiply 4 times negative 3 and I times I. We know that I squared is equal to negative 1. Therefore, negative 12 times negative 1 is positive 12. A more difficult problem here that I outlined below with 2 different methods would be how to simplify this 3 times the square root of negative 24 and 2 times the square root of negative 18. This is like 2 problems in one, and you can treat it as such. In fact, that's what I do down here. With method 1, when I just say separate and simplify, I treat this as just 2 separate problems that I then multiply at the end. The key step, as I find a nice color here to outline, the key step being that, after I break this down to the square root of 6 times the square root of 2, I then need to say to myself, there may be a perfect square in there. So multiply 6 times 2 and put it all under one roof. Because these are both square roots, I can multiply them. The square root of 12. The square root of 12 consists of the square root of 4 times 3. Okay, and the square root of 4, you see that as a perfect square. So then you can pull that out. The other method that we have is we could multiply 24 times 18. I don't know why you would want to do that. It creates a number that really creates more work for you. So just break 24 down into 4 times 6, and I break 18 down into 9 times 2. Now notice there we have 4 and 9, which are both perfect squares. So I can pull out the square root of 4, which is 2, the square root of 4, which is 2. Notice the square root of 4, which is 2. And then the square root of 9, which is 3. So that's what happens there. And the other method, method 2, please take a look at both of these and the color coding that I have. Study these to prepare yourself to move on tomorrow. Thank you for watching. And please, happy simplifying. Happy simplifying.